On the clear nights of October 2025, when we look up at the starry sky, we will witness something extraordinary that will not be repeated again in the history of humanity. Up there, moving silently among the constellations, travels an object that has been wandering through interstellar space for billions of years. Its name is 3I/Atlas, and it represents our last chance in centuries, perhaps millennia, to directly observe a visitor from another stellar system. Time is running out. Every night that passes, every hour that goes by, brings us closer to the moment when this enigmatic traveler will disappear forever from our skies. Astronomers have calculated with mathematical precision when this will happen, and the dates are set in stone by the immutable laws of celestial mechanics. Hello, and welcome to our journey through the last observable period of 3I/Atlas before its definitive return to interstellar space. Tonight, we explore why the coming weeks represent our last chance in centuries, perhaps millennia, to directly observe this visitor from another stellar system. Before we delve deeper into this unique, astronomical opportunity, take a moment to get comfortable wherever you are listening, perhaps in bed, during a quiet evening walk, or in a peaceful moment of your day. If stories like this help you relax and discover new wonders, consider subscribing or liking this show. It helps more curious minds connect with these relaxing explorations. Now, let your thoughts flow as we contemplate this historic moment in astronomy. The numbers don't lie. The 29th of October 2025 marks a crucial date in the history of 3I/Atlas. At that exact moment, the interstellar comet will reach its perihelion, the closest point to the Sun in its entire trajectory. But paradoxically, this moment of maximum solar proximity also marks the beginning of its invisibility from Earth. During the days following perihelion, 3I/Atlas will enter what astronomers call a solar conjunction. This means that from our terrestrial perspective, the comet will be hidden behind the Sun's bright disk. Imagine trying to see a lit candle while someone holds a 1,000-watt lamp directly between you and the flame. That's what 3I/Atlas will be like during October and most of November, completely invisible, lost in the solar glare. This solar conjunction will last for approximately 4 weeks. During this period, no ground-based telescope will be able to detect the comet. The only possible observations will be made by spacecraft situated at strategic points in the solar system, far from the Earth-Sun line of sight. But for us, ground-based observers, October will represent a total observational silence. The reappearance of 3I/Atlas is scheduled for late November 2025. Orbital calculations indicate that the comet will gradually emerge from the Sun's glare and become visible again in the dawn sky, specifically in the constellation of Virgo. This reappearance will mark the beginning of the final phase of observation from Earth. Why is this opportunity so special? Why do we speak of centuries or millennia before another similar chance? The answer lies in the fundamental nature of interstellar objects and their hyperbolic trajectories. 3I/Atlas follows a hyperbolic trajectory, which means it is not gravitationally bound to our Sunday. Unlike traditional comets that return periodically in elliptical orbits, this interstellar visitor is just passing through. Its velocity is so high that the Sun's gravity cannot capture it. After its close encounter with our Sun, it will continue to accelerate until it completely escapes our solar system. Computational models have plotted its future trajectory with precision. After reappearing in November, 3I/Atlas will continue to move away from the Sun and the Earth. In March 2026, it will pass near the orbit of Jupiter, receiving one last gravitational boost that will send it definitively into interstellar space. Once it crosses the heliosphere, the invisible boundary where the Sun's influence fades, 3I/Atlas will be lost forever in the depths of the cosmos. This is the sober reality of interstellar encounters. They are unique, unrepeatable events. There are no return orbits, no future appointments scheduled. When 3I/Atlas disappears into interstellar space, it will take with it all the secrets we were unable to decipher during its brief visit. To completely understand the exceptional nature of this moment, we must place it in the broader context of astronomical discoveries. Interstellar objects are extraordinarily rare. Before the discovery of Oumuamua in 2017, humanity had never consciously detected a visitor from another stellar system. Oumuamua appeared and disappeared quickly, leaving more questions than answers. 2I divided by Borisov, discovered in 2019, offered us more observation time, but it also faded away, eventually into the depths of space. Now, 3I divided by Atlas represents our third opportunity in all of human history to study an object coming from the stars. Astronomers estimate that objects like 3I divided by Atlas pass through our solar system approximately once a decade, but most are too small or too faint to be detected with our current instruments. This means that interstellar objects, large and bright enough to be studied in detail, are extraordinarily infrequent. Furthermore, the timing of its passage through the inner solar system determines the observation opportunities. If an interstellar object passes through during a time of year when it is too close to the Sun from our perspective, or if its trajectory takes it mainly through regions of the solar system that are out of our field of view from Earth, the opportunities for observation are dramatically reduced. During the remaining weeks before the solar conjunction, and then during the brief window of its reappearance, scientists from around the world are running intensive observation campaigns. Every night counts. Every hour of telescopic data is invaluable. Spectrographs are analyzing the comet's chemical composition, trying to determine which elements and compounds make up its nucleus and coma. This chemical data is like a cosmic fingerprint that can reveal information about the conditions in the stellar system, where 3I divided by Atlas was formed billions of years ago. Photometers are measuring the variations in the comet's brightness, looking for patterns that reveal its rotation period and possibly the shape of its nucleus. This data is crucial for understanding the object's physical structure and how it has been modified by its long interstellar journey. Infrared telescopes are detecting the heat the comet emits, which allows them to calculate its actual size and surface temperature. This thermal information complements observations in visible light and provides a more complete picture of the visitor's physical nature. But time is running out. With each passing day, 3I divided by Atlas gets closer to the Sun from our perspective, making it more difficult to separate its faint light from the growing solar glare. Astronomers are in a race against time, trying to extract every possible bit of information before the period of invisibility begins. There is something deeply moving about the temporary nature of this opportunity. All humans alive at this historic moment share the privilege of being able to turn our gaze to the sky and know that up there travels an object that has seen the stars from a perspective that no human has ever experienced. This comet has wandered through interstellar space, moving among the stars for eons. It has been a silent witness to cosmic events that occurred long before the Earth was formed. Its surface may have been bombarded by cosmic rays from distant galaxies, sculpted by the stellar wind of suns that died billions of years ago. And now, for a brief moment on the cosmic timescale, this ancient traveler is passing close enough to our little blue planet for us to study it, photograph it, and contemplate its presence in our night skies. The unrepeatable nature of this opportunity gives it a special emotional weight. It's not like an eclipse, which repeats in predictable cycles, or like a periodic comet that returns every few decades. This is a comet, truly once-in-a-lifetime opportunity, a cosmic moment that will not be repeated for any of us. During these final weeks of observation, every clear night becomes an invaluable gift. Meteorologists are collaborating with astronomers, providing detailed predictions of atmospheric conditions to maximize observation opportunities. Observatories around the world have reorganized their regular observation schedules to dedicate precious time to 3I divided by Atlas. The large telescopes that normally study distant galaxies or exoplanets have turned their mirrors toward this interstellar visitor, recognizing that this opportunity takes priority over almost any other astronomical project. Amateur astronomers also play an important role. With smaller telescopes, They can contribute valuable data on the comet's brightness and position. Photographs taken night after night by dedicated observers help to build a visual record of 3I divided by Atlas's passage through our solar system. Even those without telescopes can participate in this historic moment, knowing that 3I Atlas is up there, invisible to the naked eye but present, adds a special dimension to the starry October nights. It's a tangible reminder that our solar system doesn't exist in isolation, but is part of a galaxy filled with other worlds and other star systems. When 3I divided by Atlas finally disappears into interstellar space, it will carry with it a piece of human history. It will be the first interstellar object that humanity has observed for an extended period. With advanced modern technology, the data collected during its visit will be studied for decades, gradually revealing secrets about the formation of planetary systems in other parts of the galaxy. Children born in 2025 will be the last generation to live during the visit of 3I divided by Atlas. When they are older adults, they will be able to tell their grandchildren about the time when a visitor from the stars passed through our solar system. It will be a story that connects human generations with the immensity of the cosmos. The photographs and images of 3I divided by Atlas will join the iconic astronomical images that define moments in our understanding of the universe. Just as the Hubble telescope images changed our perception of the cosmos, the images of our first, well-studied interstellar visitor will mark a milestone in our understanding that we are not alone in the galaxy, at least not in the sense that other planetary systems exist that can produce objects like comets and asteroids. As we approach the end of this unique observation window, it's worth reflecting on the extraordinary privilege of living at this specific moment in human history. We are the first generation with the technology to detect and study interstellar visitors, and 3I divided by Atlas is our most generous teacher to date. The window is closing, but the knowledge we will gain will last forever. In the remaining nights before 3I divided by Atlas fades behind the sun's glare, every observation, every photograph, every spectrum collected is a treasure that humanity will cherish long after the comet has returned to the stars from which it came. And so, as the October nights advance inexorably toward the moment of solar conjunction, we watch with a mixture of fascination and cosmic melancholy, knowing that we are witnessing something that will not happen again in our lifetimes and possibly not for many future generations. The window is closing, but the memory of the encounter will remain forever etched in the history of our species and its eternal quest to understand the cosmos around us. Imagine for a moment the vastness of our planet Earth, a sphere nearly 8,000 miles in diameter, spinning in space as it orbits the Sunday. Now, imagine that from different points on this sphere, millions of people direct their gaze to the night sky, each seeing a slightly different fragment of the cosmos. This difference in perspective, which astronomers call geographic parallax, becomes crucial when we talk about observing objects like 3I divided by Atlas, especially during its final weeks of visibility. The position of your home on the Earth's surface is not just a mailing address. It's your personal window to the universe, and it determines when, where, and how well you can see this interstellar visitor during its final moments of observation from our planet. During September 2025, when 3I divided by Atlas was still visible before its disappearance behind the sun, observers in different hemispheres had completely different astronomical experiences. Those located in the Earth's southern hemisphere enjoyed privileged conditions for viewing this enigmatic object, while residents of the northern hemisphere faced considerable but not insurmountable challenges. The southern hemisphere of our planet became the front row seat for observing 3I divided by Atlas. During September, from locations like Chile, Argentina, South Africa, Australia, and New Zealand, the interstellar comet appeared higher in the night sky and for more prolonged periods each night. This advantage is not accidental. It is due to the specific geometry of 3I divided by Atlas's trajectory combined with the orientation of the Earth in its orbit. During those months, the comet was approaching the sun from a direction that placed it preferentially in the region of the sky, most easily visible from southern latitudes. In cities like Santiago, Chile, or Cape Town, 3i divided by Atlas rose above the horizon during the early hours of the night, reaching respectable heights in the sky before disappearing in the hours before dawn. This elevated position means less of the Earth's atmosphere between the telescope and the comet, resulting in sharper images and clearer observations. Observers in the southern hemisphere also benefited from more atmospherically stable nights during the austral winter months. The seeing conditions, as astronomers call them, tend to be better during the colder months, when there's less atmospheric turbulence caused by rising thermal currents. But perhaps the most significant advantage for southern observers was the available time. While observers in the northern hemisphere had observation windows of just a few hours, each night those in the south could follow 3i divided by Atlas for most of the night, from dusk until the early hours of dawn. For the millions of observers located in the northern hemisphere, September 2025 presented a more complicated but not hopeless situation. From locations like Europe, North America, much of Asia, and North Africa, 3i divided by Atlas appeared low on the southwestern horizon, visible only during the first few hours, after dusk. This low position on the horizon created several observational obstacles. First, the comet had to be observed through a greater amount of the Earth's atmosphere, which reduced its apparent brightness and degraded the quality of the images. The atmosphere acts as a natural filter, absorbing and scattering the light from celestial objects, and this effect is more pronounced when we observe objects near the horizon. Second, urban light pollution becomes especially problematic for objects low on the horizon. The lights from cities create a glow that is more intense near the horizon, where most sources of artificial light are concentrated. For urban observers in the northern hemisphere, this meant that 3i divided by Atlas was often submerged in the sky glow, invisible except to the largest telescopes or from exceptionally dark locations. Third, the observation window was frustratingly short. Many northern observers had barely 2 or 3 hours after dusk before 3i Atlas set below the western horizon. For those who worked during the day and could only observe after work, this meant limited and often missed opportunities due to cloudy weather or personal commitments. But the story doesn't end with the September disappearance. When 3i divided by Atlas reappears in late November 2025 after its period of invisibility. Due to the solar conjunction, the tables will turn dramatically. The comet will emerge in the dawn sky, specifically in the constellation of Virgo, and this time the conditions will slightly favor observers in the northern hemisphere. During December 2025, 3i divided by Atlas will be visible in the hours before dawn. Observers will need to get up early, possibly between 4 and 6 a.m., depending on their specific location, to have the best observation opportunities. The comet will appear on the eastern horizon, gradually gaining altitude as dawn approaches. This new configuration presents both unique opportunities and challenges. On one hand, observing before sunrise often benefits from more stable atmospheric conditions, as the atmosphere has had all night to cool down and settle. On the other hand, the observation window is limited by the approaching daylight, which will gradually wash out the sky and make even relatively bright objects invisible. Observers in the northern hemisphere will find that 3i divided by Atlas appears higher in their sky in the morning during December, offering better observing conditions than they had during September. This is especially true for locations at mid-latitudes, where the comet will reach respectable altitudes before the morning twilight becomes too intense. The importance of knowing your specific location cannot be underestimated when it comes to planning observations of 3i divided by Atlas. An observer in Stockholm, Sweden will have a completely different experience than someone in Madrid, Spain, even though both are in Europe. Differences in latitude of just a few degrees can translate into significant differences in the comet's altitude above the horizon and the duration of the observation window. To maximize observing opportunities, astronomers have developed specific star charts for different latitude ranges. These charts show the expected position of 3i divided by Atlas in the sky for specific dates and from particular geographic locations. Observers can use these charts to plan observing sessions, identify the best time windows, and locate the comet in the sky using nearby stars as references. Modern mobile applications have revolutionized this process. Apps like Sky Safari, Starwalk, and Stellarium can automatically calculate the position of 3i Atlas for any location on Earth and at any point in time. These digital tools eliminate much of the calculation work that previously required specialized knowledge of spherical astronomy. But digital star charts are just the beginning. Serious observers must also consider factors like local elevation and the presence of mountains or buildings that might block the view of the horizon, and the typical local weather conditions during the observation dates. Not all places on Earth are equal. When it comes to astronomical observation, modern light pollution has created a complex map of favorable and unfavorable locations for astronomy. To observe 3i divided by Atlas, especially given its relatively faint brightness, the choice of observation location can be the difference between success and disappointment. The ideal places to observe 3i divided by Atlas share several characteristics. First, they are far from large urban centers and their respective light pollution domes. Second, they have clear horizons in the relevant directions, without mountains, tall trees, or buildings blocking the view. Third, they benefit from stable weather conditions with frequent clear skies during critical observation periods. Some of the best sites in the world to observe 3i divided by Atlas include the Atacama Desert in Chile, the highlands of Namibia, the Australian outback, the Canary Islands, and certain locations in the southwestern United States. These places combine exceptional dark skies with stable atmospheric conditions and clear horizons. But you don't need to travel to exotic destinations to have successful observing opportunities. Many more accessible locations can offer suitable conditions for observing 3i divided by Atlas with the appropriate equipment. National parks, nature reserves, and even rural areas relatively close to cities can provide skies that are dark enough to allow for satisfactory observations. Temporal coordination is crucial when observing 3i divided by Atlas from different geographic locations. The comet doesn't appear at the same time in all locations. Its rise and set times vary depending on the observer's longitude. An observer in London will see 3i divided by Atlas emerge from the eastern horizon about an hour before someone in New York, simply due to the Earth's rotation. This time difference can be leveraged by geographically distributed groups of observers, observatories, and amateur astronomers in different time zones who can coordinate their observations to create nearly continuous coverage of 3i divided by Atlas. During critical observation periods, when the comet sets for observers in Europe, it is rising for observers in the Americas. During the reappearance phase in November and December, this temporal coordination becomes even more important. The pre-dawn observation windows are inherently short, limited by the growing brightness of the morning sky. Observers must carefully calculate the optimal time to begin their observations, balancing the need for 3i divided by Atlas to be high enough above the horizon, with the need to complete observations before daylight renders the comet invisible. The global nature of the opportunity to observe 3i divided by Atlas has led to unprecedented international collaborations between professional and amateur astronomers. Networks of observers distributed all over the world are coordinating their efforts to maximize observational coverage of the comet during its final weeks of visibility. These networks leverage the geographical differences in observing conditions. When weather prevents observations in one region, observers in other parts of the world can compensate. When 3i divided by Atlas is unobservable from one hemisphere due to its position in the sky, the other hemisphere can continue collecting data. The data collected by this global network of observers is combined to create a more complete picture of the behavior and characteristics of 3i divided by Atlas during its passage through our solar system. Brightness measurements taken from different locations help to build more accurate light curves. Images taken from different angles provide information about the comet's shape and orientation. The digital age has made this global coordination possible in ways that would have been unthinkable just a few decades ago. Observers can instantly share images, data, and observations through online platforms. Weather Forecasts for observing sites around the world are available in real time, allowing observers to plan their sessions with precision. Observers in different parts of the world need specific preparations, tailored to their local geographical conditions. In tropical regions, where nights are consistently about 12 hours long year-round, observers have relatively stable windows for observation. However, they must also contend with higher atmospheric humidity and the possibility of frequent cloud formation. At higher latitudes, especially during the northern hemisphere winter, when 3I divided by Atlas reappears, observers face very long nights, but also extremely cold temperatures. Equipment must be protected against condensation and freezing. Camera and other electronic device batteries drain more quickly in cold temperatures. Observers in desert regions benefit from exceptionally clear and dry skies, but must prepare for large temperature fluctuations between day and night. Optical equipment may require time to acclimate to the nighttime temperatures to avoid condensation issues. Coastal regions often experience variable seeing conditions due to the temperature differences between the land and water. Coastal observers must be especially careful about wind direction and local meteorological conditions that can affect the quality of observations. As we prepare for the last opportunities to observe 3I divided by Atlas, geography becomes destiny. Your location on this blue planet determines your unique experience with this cosmic visitor. From the Andean highlands to the Siberian plains, from the Australian coasts to the African deserts, millions of human eyes will turn to the sky during these critical weeks, each seeing 3I divided by Atlas from their own unique perspective in the cosmos. And when the comet finally disappears into interstellar space, it will carry with it not only the secrets of its origin, but also the memories shared by a humanity united for a moment in its common quest to understand the universe around us. What does it take to see an object that has traveled from the stars? This seemingly simple question hides a fascinating complexity that connects the most sophisticated human engineering with our most primitive desire to understand the cosmos. In the case of 3I divided by Atlas, the answer isn't as straightforward as we might expect from a typical comet. Unlike the great comets that occasionally grace our skies with their spectacular tails visible to the naked eye, 3I divided by Atlas presents a considerable observational challenge. Its apparent brightness fluctuates between magnitude 10 and 13, figures that may seem arbitrary to those uninitiated in astronomy, but which in reality define the boundary between what is visible and invisible to the human eye. To put these figures into perspective, consider that the faintest star visible to the naked eye from a dark location has a magnitude of about 6. Each increment on the magnitude scale represents a decrease in brightness by a factor of about 2.5 times. This means that 3I divided by Atlas, with its magnitude between 10 and 13, is between 15 and 4,000 times fainter than the most faintest star you can see without optical aid. Binoculars, those faithful companions of many amateur astronomers, meet their limit here. Even the most powerful binoculars, typically 7x50 or 10x50, can reveal objects down to about magnitude 9 or 10 under exceptional conditions. For 3I divided by Atlas, fluctuating in the magnitude 10 to 13 range, binoculars simply don't gather enough light to make this elusive interstellar visitor visible. This limitation is not a design flaw in binoculars. It's determined by the fundamental laws of optics. The amount of light an instrument can gather depends on the area of its aperture, the front opening where light enters. Larger binoculars typically have objective lenses about 2 inches in diameter, while the telescopes used to observe 3I divided by Atlas require apertures of at least 10 inches and preferably larger. This difference in light gathering area is dramatic. A 10-inch telescope has a light gathering area 25 times greater than 2-inch binoculars. In terms of the ability to see faint objects, this translates to about a 3.5 magnitude difference in the detection limit. To successfully observe 3I divided by Atlas, you need a telescope with a minimum aperture of 10 inches, though 11 inches or more will provide a considerably better experience. These telescopes, commonly referred to as 10 or 11-inch instruments, represent the entry point into the world of faint object astronomy. The type of telescope also matters. Newtonian reflectors, with their simple and efficient design, are popular for this type of observation due to their excellent value. A 10-inch Newtonian reflector can be purchased for a fraction of the cost of a refractor or compound telescope of similar aperture, although it requires occasional collimation. Schmidt-Cassegrain and Maksutov-Cassegrain telescopes, while more expensive, offer advantages in portability and ease of use. Their compact design makes them more manageable for observers who need to transport their equipment to dark sky sites. For 3I/Atlas, any of these designs will work adequately, provided the aperture is sufficient. The telescope's mount deserves special consideration when observing objects like 3I/Atlas. A motorized equatorial mount is practically essential for long-duration tracking. 3I/Atlas moves slowly against the background of stars, but during observation sessions lasting several hours, this motion becomes noticeable. A mount that can automatically track the comet's motion frees the observer to concentrate on viewing or photography. The digital age has radically transformed the experience of locating and tracking objects like 3I/Atlas. Modern mobile apps have democratized access to astronomical information that previously required specialized calculations and printed ephemerides. Sky Tonight stands out as one of the most accurate apps and up-to-date for tracking 3I/Atlas. The application receives regular orbital updates based on recent telescopic observations, which means its position predictions are extraordinarily accurate. Users can configure alerts to be notified when 3I/Atlas is in an optimal position for observation from their specific location. Sky Tonight's augmented reality feature allows users to point their mobile devices at the sky and see a digital overlay showing the exact position of 3I/Atlas in real time. This functionality is invaluable when trying to locate such a faint object in a complex field of stars. Sky Safari Pro offers even more advanced capabilities, including the ability to directly control incompatible motorized telescopes. Users can select 3I/Atlas in the app and send positioning commands directly to their telescope, automating the process of locating it, which traditionally required star charts and manual navigation. Stellarium Mobile provides detailed visual representations of the star field around 3I/Atlas, showing reference stars, down to very faint magnitudes. This is particularly useful for confirming that you've located the correct object, since 3I/Atlas can be indistinguishable from nearby faint stars without reference to detailed star charts. Understanding celestial coordinates becomes crucial when you're looking for an object as faint as 3I/Atlas. The equatorial coordinate system, based on right ascension and declination, provides a reference frame that is stable for locating objects in the sky. Mobile apps calculate these coordinates automatically, but understanding how to use them manually provides a deeper understanding and a backup option if the technology fails. Right ascension is measured in hours, minutes, and seconds, corresponding to the Earth's rotation. Declination is measured in degrees, minutes, and seconds, corresponding to the angular distance north or south of the celestial equator. For 3I/Atlas, these coordinates change slowly each day due to the comet's orbital motion. Detailed ephemerides, available on specialized websites and apps, provide daily updated coordinates. Serious observers often print out these coordinates as a backup for their mobile apps. Star hopping is a traditional technique that involves using known star patterns as guideposts to locate faint objects. For 3I/Atlas, this typically involves identifying nearby bright stars and then using detailed charts to navigate through fainter star fields to the comet's position. Photographing 3I/Atlas requires specialized techniques, adapted for faint and moving objects. Traditional deep sky astrophotography methods must be modified to accommodate the comet's orbital motion and its relatively low brightness. Individual exposures for 3I/Atlas typically range between 5 and 15 minutes, depending on the telescope's aperture and the camera's sensitivity. Longer exposures can result in star trailing if the mount isn't perfectly polar aligned, but shorter exposures may not collect enough light to show the comet clearly. The technique of stacking becomes essential for getting quality images of 3I divided by Atlas. Multiple exposures are digitally combined to improve the signal-to-noise ratio, revealing details that would be invisible in individual exposures. However, the comet's motion complicates this process, since the stars and the comet are moving at different speeds. Stacking with comet motion compensation is an advanced technique where the images are aligned, based on the comet's position rather than the background stars. This results in a sharp comet against a background of star trails, but it better reveals details of the coma and any structure in the comet's tail. Optical filters. Optical filters can significantly improve the visibility of Tsuchinshan-ATLAS under certain conditions. Broadband filters, like light pollution reduction filters, can help improve the contrast between the comet and the sky glow in locations affected by light pollution. More specifically, narrowband filters can reveal specific spectral features of Tsuchinshan-ATLAS. Filters that transmit the wavelengths of diatomic carbon can emphasize the comet's characteristic green color, while filters that block the sodium spectral lines from streetlights can improve the overall contrast. O3, or doubly ionized oxygen, and hydrogen beta filters can also be useful, although their effectiveness depends on the specific composition of the gases in the coma of Tsuchinshan-ATLAS. Experimenting with different filters can reveal aspects of the comet that are invisible in white light. Success in observing Tsuchinshan-ATLAS depends as much on equipment preparation as it does on observing conditions. Telescopes, especially reflectors, require regular collimation to maintain their optimal optical performance. Poor collimation can significantly reduce the ability to detect faint objects. Cleaning the optics is equally important. Dust, moisture, or smudges on the lenses or mirrors can scatter light and create halos that mask faint objects like Tsuchinshan-ATLAS. However, excessive cleaning can also damage delicate optical coatings, so it should only be done when absolutely necessary. Temperature conditions affect the telescope's performance. Mirrors and lenses need time to acclimate to the outside temperature to avoid internal thermal currents that degrade the image quality. For Tsuchinshan-ATLAS, where every photon counts, this thermal acclimation can be the difference between detection and non-detection. Batteries and electronics also require special attention during long nighttime observing sessions, which are typically necessary to find and track Tsuchinshan-ATLAS. Low temperatures reduce battery capacity, and condensation can damage sensitive electronics. Experienced observers carry spare batteries and protect their electronic equipment with dew heaters when necessary. Observing Tsuchinshan-ATLAS is not a solitary activity. Networks of amateur and professional astronomers share information in real time about the best observation strategies, changes in the comet's brightness, and successful observing conditions from different geographical locations. Online forums specializing in cometary astronomy provide regular updates on the observational status of Tsuchinshan-ATLAS. Observers share images, brightness reports, and technical tips that benefit the entire community. This distributed collaboration greatly amplifies individual observing capabilities. Social media has created channels for immediate communication between observers. When someone confirms a visual detection of Tsuchinshan-ATLAS from their location, they can instantly alert observers in similar locations or with comparable equipment. This real-time feedback is invaluable for maximizing opportunities for successful observation. Citizen science projects also incorporate observations of Tsuchinshan-ATLAS into their databases. Amateur observers contribute photometric, astrometric, and morphological measurements that complement professional observations. These contributions become part of the scientific record of the comet's passage through our solar system. As Tsuchinshan-ATLAS continues its trajectory toward interstellar space, observing conditions constantly evolve. Its apparent brightness changes due to variations in its distance from both the Sun and the Earth. Its position in the sky shifts against the stellar background, requiring constant adjustments in tracking strategies. Successful observers adapt their techniques based on current reports of the comet's conditions. If recent reports indicate that Tsuchinshan-ATLAS has brightened due to increased cometary activity, they can attempt observations with smaller equipment or from locations with more light pollution. Conversely, if the comet has faded, they may require larger telescopes or more sophisticated techniques. The comet's changing morphology also influences observation techniques. As Tsuchinshan-ATLAS develops or loses cometary structure, different filters or imaging techniques can become more or less effective. Observers must stay informed about these developments to adapt their methods as needed. Weather and local atmospheric conditions add another layer of variability that observers must navigate. Weather forecasting apps specialized for astronomy help observers plan observing sessions during windows of clear sky. Atmospheric transparency, seeing, and relative humidity all affect the ability to detect faint objects like Tsuchinshan-ATLAS. As we approach the final opportunities to observe Tsuchinshan-ATLAS, the tools we use to touch the infinite become more precious. Every telescope aimed at this interstellar visitor, every mobile app that calculates its position, every filter that reveals its true nature represents the culmination of centuries of human engineering and scientific curiosity. These tools are our extensions into the cosmos, allowing us to participate in a moment that will not be repeated in our lifetimes. And when Tsuchinshan-ATLAS finally fades, beyond the reach of our most powerful instruments, it will carry with it not only the secrets of its stellar origin, but also a testament to our human ability to create the tools that allow us to touch, however briefly, the infinite. Tsuchinshan-ATLAS is breaking the rules in the orderly world of cometary astronomy, where decades of observation have established predictable patterns of behavior. This interstellar visitor presents itself as a fascinating anomaly that challenges our most basic expectations of how a comet should behave. Its intense green color is the first thing that captivates the attention of any lucky observer. It's not the soft green of typical comets, but a bright, distinctive green that is due to exceptionally intense diatomic carbon emissions. This spectral feature, though not unique in the cometary world, appears in Tsuchinshan-ATLAS with an intensity that far exceeds what is considered normal. Spectrographs mounted on telescopes around the world have confirmed that the diatomic carbon emission lines in the spectrum of Tsuchinshan-ATLAS are extraordinarily prominent. These lines, centered around 510 nanometers in the visible spectrum, are responsible for the characteristic green glow that distinguishes the comet even in relatively short exposure photographs. But the color is just the first hint that this object doesn't behave as we would expect from a conventional comet. The anomalies extend to virtually every aspect of its observed nature, from its chemical composition to its activity pattern, creating a scientific puzzle that continues to intrigue researchers. Spectroscopic analysis of Tsuchinshan-ATLAS has revealed a chemical composition that seems more typical of exotic interstellar environments than of an object formed in a typical planetary system. The ratio of carbon dioxide to water in its coma is approximately 8:1, a proportion that challenges all existing models of cometary formation. In solar system comets, water typically dominates the preferred, volatile composition, with carbon dioxide present in much smaller amounts. This relative abundance of water reflects the temperature and pressure conditions in the regions of the protoplanetary disk where these comets formed. But Tsuchinshan-ATLAS suggests a completely different formation environment. The high concentration of carbon dioxide could indicate formation in the cold, outer regions of a planetary system where temperatures were low enough to allow for the efficient condensation of solid carbon dioxide. Alternatively, it could suggest formation in an interstellar environment where condensation processes operate under very different conditions than those prevailing in protoplanetary disks. Even more intriguing is the detection of atomic nickel in the spectrum of Tsuchinshan-ATLAS. Atomic nickel is extremely rare in solar system comets, where it typically appears only in trace concentrations and is usually accompanied by iron in proportions that reflect their relative abundance in meteoritic materials. In Tsuchinshan-ATLAS, the nickel, it appears as a prominent spectral feature without the corresponding iron lines that would be expected based on standard cosmic abundances. This nickel anomaly has generated considerable debate in the astronomical community. with some researchers suggesting that it could indicate unique chemical differentiation processes in 3I divided by Atlas's parent body. Others propose that the nickel lines could be evidence of irradiation processes during the comet's long interstellar journey. Solar system comets exhibit predictable activity patterns based on their distance from the Sun. Typically, they begin to show cometary activity when they are between 3 and 5 astronomical units from the Sun, as solar heat begins to sublimate the surface ices. 3I divided by Atlas, however, began to show significant activity when it was still more than 6 astronomical units from the Sunday. This early activity is particularly noteworthy because it suggests that 3I divided by Atlas contains volatiles that sublimate at lower temperatures than those typically found in solar system comets. Candidates include carbon monoxide, molecular nitrogen, or even molecular hydrogen, all of which can sublimate at the cold temperatures that prevail in the outer regions of the solar system. The activity pattern of 3I divided by Atlas also differs from what is observed in typical comets. Instead of a steady increase in activity, as it approaches the Sun, 3I divided by Atlas has shown erratic fluctuations in its brightness and in its coma production. These changes seem to be correlated with its rotation, suggesting discrete active areas on the surface that face the Sun at different times. The morphology of 3I divided by Atlas's coma also exhibits unusual features. High-resolution images taken with large ground-based telescopes show an asymmetrical structure in the coma, with concentrations of material that do not follow the expected symmetrical patterns of uniform sublimation. This asymmetry could indicate complex surface topography, variations in surface composition, or the effects of non-uniform rotation. To fully understand what makes 3I divided by Atlas special, we must compare it with its interstellar predecessors, Oumuamua and 2I divided by Borisov. Each of these objects has contributed to our understanding of these interstellar visitors, but each has also raised unique questions. Oumuamua, discovered in 2017, was characterized by its extremely elongated shape and its lack of observable cometary activity. Its non-gravitational behavior, evidenced by small accelerations not explainable by solar gravity alone, generated speculation about its nature and composition. However, Oumuamua passed through our solar system so quickly that opportunities for detailed study were limited. 2I divided by Borisov, discovered in 2019, behaved more like a conventional solar system comet. It showed a typical coma and tail, and its spectrum revealed chemical compositions that, although distinct, were not completely alien to what is observed in local comets. Borisov provided the first opportunity to study a genuine interstellar comet for an extended period. 3I divided by Atlas combines aspects of both predecessors while introducing completely new features. Like Oumuamua, it shows behaviors that defy expectations based on solar system objects. Like Borisov, it exhibits clear cometary activity that allows for detailed spectroscopic analysis. But unlike both, 3I divided by Atlas presents chemical and morphological anomalies that have no clear precedence. The speed of 3I divided by Atlas also sets a new record. With a heliocentric velocity of approximately 36 miles per second, it surpasses both Oumuamua and Borisov. This high speed suggests a more distant origin, or a more complex dynamic history involving gravitational encounters with massive objects during its interstellar journey. The extraordinary speed of 3I divided by Atlas raises fundamental questions about its history and origin. Objects that form in typical planetary systems and are then ejected by gravitational interactions normally reach escape velocities of 12 to 18 miles per second. The much higher speed of 3I divided by Atlas suggests additional acceleration processes. One possibility is that 3I divided by Atlas was accelerated by gravitational encounters with stars during its interstellar journey. Calculations show that a close encounter with a typical star could accelerate an object like 3I divided by Atlas to the observed speeds. However, such encounters are statistically rare, which would make 3I divided by Atlas an extraordinarily lucky or unlucky object depending on your perspective. Another explanation could involve 3I divided by Atlas originating in a more exotic stellar environment. If it formed near a massive binary star or was ejected during a supernova explosion, it could have acquired initial velocities, much higher than those typical of normal planetary ejections. The high speed also has implications for the future trajectory of 3I divided by Atlas. Once it leaves our solar system, it will continue to move through interstellar space at a speed that will carry it to very distant regions of the galaxy on relatively short timescales. In about 1 million years, 3I divided by Atlas could be in a completely different region of the Milky Way. The anomalous characteristics of 3I divided by Atlas have profound implications for our understanding of how planetary systems form in different parts of the galaxy. If 3I divided by Atlas is representative of objects formed in stellar environments different from our solar system, it suggests that a much greater diversity exists in planetary formation processes than we had previously appreciated. The carbon dioxide-rich chemical composition of 3I divided by Atlas could indicate formation in a planetary system with a very different thermal history from that of our solar system. Planetary formation models predict that the relative abundance of different chemical species in comets should reflect the temperature and pressure conditions in the protoplanetary disk where they formed. If 3I divided by Atlas formed in a system with a star of a different mass, or in an environment with a different elemental abundance, this could explain its unique chemical characteristics. Alternatively, it could have formed at a very different time in galactic history, when the elemental abundances in the interstellar medium were significantly different from today's. The detection of atomic nickel without corresponding iron is particularly intriguing from this perspective. In the solar system, nickel and iron are found typically in proportions that reflect their abundance in primordial nebular material. The absence of iron in the spectrum of 3I divided by Atlas could indicate chemical differentiation processes that do not operate in our solar system or formation conditions that favor the selective retention of nickel. During its long journey through interstellar space, 3I divided by Atlas has been exposed to very different conditions than those experienced by solar system objects. Cosmic radiation, the interstellar wind, and occasional encounters with interstellar gas and dust clouds may have significantly modified its surface and composition. Irradiation by cosmic rays over millions or billions of years could have altered the surface chemistry of 3I divided by Atlas. Cosmic rays can break down complex molecules, create exotic chemical species, and modify the physical properties of surface materials. These processes could explain some of the chemical anomalies observed in the comet's spectrum. Bombardment by high-energy particles could also have created an altered layer on the surface of 3I divided by Atlas that is chemically different from the interior material. When cometary activity began to sublimate surface material, this altered layer might have been the first to be released, explaining the unusual spectral features observed during the early phases of activity. Encounters with interstellar clouds during 3I divided by Atlas's journey could have deposited foreign material on its surface. The interstellar medium contains a variety of complex organic molecules, ices, and dust grains that could adhere to the surface of an object traveling through it. The subsequent sublimation of these deposited materials could contribute to the anomalous spectral features. Photometric observations of 3I divided by Atlas have revealed periodic variations in its brightness that suggest rotation, but the object's rotation period and geometry remain enigmatic, and the brightness variations show a complex modulation that cannot be easily explained by the simple rotation of a regularly shaped object. One possibility is that 3I divided by Atlas has a highly irregular shape with surface areas of different reflectivities that are presented to the observer as the object rotates. This could create the complex pattern of brightness variations observed. Alternatively, the object could have a complex rotational state, such as tumbling, which combines rotation around multiple axes. The presence of cometary activity further complicates the rotation analysis. Jets of ejected material can create torques that alter the object's rotational state over time. If 3I divided by Atlas has active jets located in specific areas of its surface, these could be modifying its rotation in ways that are difficult to predict. Light curve studies of 3I divided by Atlas continue to refine estimates of its rotation period, but the presence of variable activity and possible precession makes determining a single period extremely challenging. This uncertainty limits our ability to infer the object's shape and orientation, which are important parameters for understanding its history and evolution. As 3I divided by Atlas continues its approach to the Sun, and then moves away during the post-perihelion phase, the lighting and activity conditions will change, potentially revealing new aspects of its composition and behavior. Spectrographs continue to monitor the object, looking for changes in emission lines that could indicate the sublimation of different chemical species. The period immediately after perihelion could be particularly revealing if 3I divided by Atlas contains volatile species that sublimate only at high temperatures. These might appear in the spectrum only after maximum solar heating. Compounds like metallic sulfides, silicates, or even refractory metals could contribute to the spectral features in this phase. Changes in the coma's morphology could also reveal information about the internal structure and distribution of volatile materials on 3I divided by Atlas. If different regions of the object contain different concentrations of volatile materials, this could manifest as changes in the shape and orientation of the coma. As different areas face the Sunday infrared, observations are particularly valuable for understanding the thermal and compositional nature of 3I divided by Atlas. Infrared telescopes can detect the thermal signatures of specific minerals and organic compounds that are invisible in visible light. These observations can provide information that complements optical spectral studies. As 3I divided by Atlas continues to defy our expectations and break the established rules of cometary behavior, each new observation adds another piece to the puzzle of its extraordinary nature. This green visitor is not just another interstellar comet. It's a window into formation and evolution processes that operate on galactic scales, a chemical messenger from stellar environments we might never visit directly. Its anomalies are not flaws to be explained away, but clues to the diversity and complexity of the processes that form planetary objects throughout the cosmos. And when it finally fades into the depths of interstellar space, it will carry with it secrets that will continue to influence our understanding of planetary formation and interstellar chemistry for decades to come. At the Paranal Observatory, in the heart of the Atacama Desert, 4 giant telescopes point toward the same small region of the night sky. Their mirrors, each 8.2 meters in diameter, collect photons that have traveled from the depths of interstellar space. Tonight, like so many others in recent weeks, they are dedicated to an urgent mission: to extract every possible bit of information from 3I divided by Atlas before it disappears forever. The Very Large Telescope has dedicated 37.5 hours of observation time to this cosmic visitor, an extraordinary allocation that reflects the unique scientific importance of this opportunity. Each hour of telescope time on these instruments is worth thousands of dollars and is normally reserved for the most promising projects in global astronomy. That so much time has been dedicated to a single object underscores the exceptional rarity of this scientific opportunity. But time is inexorably running out. With each passing night, 3I divided by Atlas gets closer to the Sun. From our perspective on Earth, until the Sun's glare makes it impossible to distinguish the comet's faint light from the daytime glare. Astronomers are in a race against time, and time is winning. The world's leading observatories have rearranged their regular schedules to accommodate emergency observations of 3I divided by Atlas. Projects that had waited months or years for observation time have been postponed. Studies of distant galaxies, searches for exoplanets, and stellar mapping have all yielded priority to this soon-to-vanish interstellar visitor. The James Webb Space Telescope, the crown jewel of modern astronomy, has aimed its 6.5-meter golden mirror toward 3I divided by Atlas on multiple occasions. The spectroscopic infrared observations from Webb can penetrate the cometary dust and reveal the chemical composition of the solid nucleus information that is impossible to obtain from ground-based telescopes. Webb's data are revealing aspects of 3I divided by Atlas that remained hidden in visible light observations. The near-spec integral field spectrograph has detected absorption lines from complex organic molecules in the comet's surface ice. These molecules, preserved during the long interstellar journey, are like chemical fossils that can reveal the conditions in the stellar system where 3I divided by Atlas formed billions of years ago. Simultaneous observations from multiple ground-based telescopes are building a three-dimensional map of 3I divided by Atlas's coma. Each telescope sees the comet from a slightly different angle due to their geographical separation, and this difference in perspective allows astronomers to reconstruct the actual spatial structure of the gas and dust cloud surrounding the nucleus. One of the most intriguing aspects of the scientific study of 3I divided by Atlas involves analyzing its isotopic composition. Isotopes are variants of chemical elements that have the same number of protons but different numbers of neutrons. The relative proportions of different isotopes in an object can reveal detailed information about the environment where it formed. In our solar system, isotopic ratios are relatively consistent, reflecting the homogeneous conditions in the primordial solar nebula. If 3I divided by Atlas formed in a different stellar system or in a different era of galactic history, its isotopic ratios could be detectably different from those we see in solar system objects. High-resolution spectrographs are specifically looking for spectral lines of rare isotopes of carbon, oxygen, and nitrogen in 3I divided by Atlas's coma. These measurements require extreme sensitivity, as the isotopic lines are typically much fainter than the lines of the main isotopes. Every clear night of observation is precious for accumulating enough light for these subtle measurements. Preliminary results suggest that the isotopic ratios in 3I divided by Atlas may be slightly different from solar ratios, although the error bars are still large. If confirmed, this would provide direct evidence that 3I divided by Atlas formed in a chemical environment distinct from that of our solar system. As 3I divided by Atlas approaches its closest proximity to the Sun on October 29th, the sublimation rate of ices from its surface increases exponentially. This intensification of cometary activity offers unique opportunities to study processes that are normally too slow to detect in more distant objects. Automated photometers are monitoring 3I divided by Atlas's brightness every few hours to detect sudden changes that could indicate outbursts of activity or the exposure of new surface materials. These continuous photometric measurements are revealing that the activity of 3I divided by Atlas is highly variable, with sudden increases in brightness lasting from hours to days. The coma's morphology is also evolving rapidly. Images taken just a few hours apart show dramatic changes in the distribution of dust and gas around the nucleus. Directional jets appear and disappear, suggesting that sublimation is occurring from specific areas on the surface that face the Sun as the object rotates. Computational models are trying to keep pace with these observations, calculating how the changing conditions of solar illumination affect the surface temperature and sublimation rates. These models are crucial to interpret the observations and extrapolate what we might expect during the later phases of the solar encounter. A critical question about 3I divided by Atlas is how much mass it's losing during its passage through the inner solar system. This information is not only important for understanding the evolution of the object itself, but also for predicting how similar objects might behave during future interstellar encounters. Direct measurements of mass loss require spectroscopic observations. Detailed observations of the coma's gas production combined with measurements of the spatial distribution of dust. Astronomers are using techniques that involve analyzing multiple emission lines to calculate the total gas production rate and then infer the total mass loss based on models of the nucleus's composition. Preliminary results suggest that 3I divided by Atlas is losing mass at a rate of approximately 2,200 pounds per second during periods of peak activity. This rate is comparable to that of similarly sized solar system comets during their perihelion approaches, but the anomalous chemical composition of 3I divided by Atlas makes these comparisons complicated. Mass loss measurements are also important to assess how much of the original object will remain when it leaves the solar system. If the mass loss rates remain high during the post-perihelion period, 3I divided by Atlas could be significantly reduced in size by the time it returns to interstellar space. Determining the rotation period and internal structure of 3I divided by Atlas represents one of the most complex observational challenges of the current scientific campaign. The object's brightness variations caused by its rotation are complicated by the presence of variable cometary activity, which can mask or mimic the rotational signals. Astronomers are using sophisticated photometric techniques involving multiple filters and wavelengths to separate brightness variations due to rotation from those caused by changes in cometary activity. This separation requires continuous observations over multiple nights to establish reliable periodic patterns. Rotation measurements can also provide clues about the object's internal structure. A solid, monolithic object will rotate differently than a loose collection of debris held together by weak gravity. Subtle changes in the rotation period can indicate internal mass redistribution due to the sublimation of ices or the migration of loose materials. Polarimetry studies are adding another dimension to these structural analyses. The light reflected from 3I divided by Atlas is slightly polarized, and this polarization changes in specific ways, depending on the object's orientation and its surface properties. These measurements can reveal information about the surface texture, particle size distribution, and the presence of materials with distinct optical properties. One of the most intriguing possibilities is that 3I divided by Atlas might not be a single object, but a binary or multiple system. Interstellar objects could retain gravitational companions during their long journeys, especially if they started as binary systems in their home star systems. The largest telescopes are conducting systematic searches for faint objects near 3I divided by Atlas that could be natural satellites or detached fragments. These searches require sophisticated image processing techniques to detect objects much fainter than the main comet against the background of stars. So far, no confirmed companions of 3I divided by Atlas have been detected, but the searches continue, becoming more refined as image analysis techniques improve. The detection of a satellite would provide invaluable information about the main object's density and internal structure, as well as insight into the dynamic processes in its home star system. Detached fragments are also of considerable scientific interest. If 3I divided by Atlas is losing pieces of its nucleus due to thermal stress or cometary activity, these fragments could provide direct samples of the object's interior. The fragments would follow trajectories slightly different from the main objects, creating extended observation opportunities even after the main comet becomes unobservable. The urgent nature of the 3I divided by Atlas observations has led to an unprecedented international scientific collaboration. Data from telescopes around the world are being shared in real time through centralized databases, allowing researchers to combine observations to maximize the scientific output. The International Astronomical Union has established a specific working group to coordinate observations of 3I divided by Atlas and ensure there is no unnecessary duplication of effort. This group is prioritizing observations based on the comet's changing conditions and the rapidly closing windows of opportunity. Atmospheric prediction models are being used to optimize observation scheduling. Sites with the best predicted conditions for specific nights are given priority for critical observations. This weather coordination is maximizing the efficiency of the global observational campaign. Preliminary scientific results are being shared via electronic circulars and online databases, much more quickly than is normal in astronomy. The urgency of the situation has compressed the typical scientific publication timelines, with important results being disseminated to the scientific community in a matter of days rather than months. Although most of the current scientific attention is focused on pre-perihelion observations, astronomers are also preparing for the post-perihelion phase, when 3I divided by Atlas reappears in November. This phase will present unique scientific opportunities, but also different observational challenges. After perihelion, 3i divided by Atlas will be moving away from both the Sun and the Earth, which means it will fade rapidly. However, the observation geometry will be different, potentially revealing aspects of the comet that were not visible during its approach. The post-perihelion coma could show asymmetrical structures caused by recoil effects from sublimation. Telescopes are being reconfigured for the post-perihelion observing conditions. The optimal filters and instruments for observing a rapidly fading object are different from those used to study an object that is gradually brightening. The most sensitive detectors are being reserved for this critical phase. Post-perihelion brightness predictions are highly uncertain because they depend on how much cometary activity persists after maximum heating. Models suggest that 3i divided by Atlas could maintain detectable activity for several weeks after perihelion, but the exact duration will depend on factors such as the composition of the nucleus and the efficiency of internal heat conduction. Even as observations continue, scientists are already analyzing the existing data and building the scientific legacy that 3i divided by Atlas will leave for humanity. The first scientific papers are being prepared, although most will wait until the observational campaign is complete to include the full dataset. The measurements from 3i divided by Atlas are being systematically compared with theoretical models of interstellar object formation. These comparisons are revealing which models are consistent with the observations and which need revision. The result will be a refined understanding of the processes that create and shape objects like 3i divided by Atlas. The data are also being carefully archived for future generations of scientists. Analysis techniques will continue to improve, and the observations of 3i divided by Atlas could reveal new secrets, decades after the object itself is long gone. These data archives will become permanent resources for research on interstellar objects. The observation protocols developed for 3i divided by Atlas are also setting precedents for future interstellar visitors. The lessons learned about how to optimize observations of faint, fast-moving objects will inform the strategies for studying the next interstellar objects we discover. As the clock ticks inexorably toward the moment when 3i divided by Atlas will disappear behind the sun's glare, every clear night becomes a precious and irreplaceable opportunity. Astronomers around the world are working with the urgency of those who know this opportunity will not come again in their lifetimes in laboratories and observatories, in offices lit by the glow of computer monitors and under the domes of open telescopes. To the night cosmos, the human race is racing against time to unravel the secrets of our interstellar visitor before it returns forever to the stars from where it came. In the silent hours before dawn, as the last stars fade into the morning twilight, astronomers around the world share a strange mix of triumph and melancholy. For months, they have pursued 3i divided by Atlas across the night sky. They have extracted its secrets with instruments of exquisite precision and have documented every aspect of its passage through our solar system. And now, as they prepare for the final observations before this cosmic visitor fades away forever, they face a sobering reality. What we don't learn now, we may never know. This is the unique nature of interstellar encounters. Unlike planets, which remain available for continuous study, or periodic comets that return in predictable cycles, interstellar objects offer windows of opportunity that open once and then close forever. 3i divided by Atlas will carry with it into the depths of the cosmos a treasure trove of information that humanity had the chance to discover, but also secrets that will remain hidden forever. The legacy of this encounter will extend far beyond the moment when 3i and Atlas disappear from our most powerful telescopes. The data collected during its visit will continue to be analyzed for decades. The techniques developed to study this object will inform the search for and characterization of future interstellar visitors, and perhaps, most importantly, the experience of directly observing an object from another star system will have changed our perspective on our place in the galaxy in ways we are only just beginning to understand. To fully appreciate the historical significance of witnessing 3i divided by Atlas, we must consider the astronomical odds that made this encounter possible. Current models of the population of interstellar objects suggest that objects the size of 3I divided by Atlas pass through our solar system, approximately once per decade. However, most of these passages occur without detection. The successful detection of an interstellar object depends on multiple factors that must align almost perfectly. The object must be large enough to reflect or emit detectable light. Its trajectory must bring it close enough to the sun to become active, but not so close that it's destroyed by tidal forces. It must pass during a time of year when it is observable from Earth, during the hours of darkness, and crucially, it must be discovered by one of our sky survey systems. While it is still far enough away to allow for months of detailed observation, the odds of all these factors aligning simultaneously are extraordinarily small. Astronomers estimate that only 1 in every 50 to 100 interstellar objects that pass through our solar system are successfully detected and studied. This means that 3I divided by Atlas represents not just an interstellar visitor, but a cosmic lottery winner that offered us the chance to study it in detail. This statistical rarity is heightened when we consider that we live in the first era of human history, in which we have the necessary technology to detect and characterize interstellar objects. If 3I divided by Atlas had visited our solar system just 50 years ago, it would have passed completely unnoticed. Its visit would have been a cosmic event without conscious witnesses, a historical moment lost forever. The data collected from 3I divided by Atlas are providing unique insights into the processes of planetary formation in star systems very different from our own. The comet's anomalous chemical composition, especially its high carbon dioxide to water ratio and the presence of atomic nickel without corresponding iron, suggests formation conditions that have no analogs in our solar system. This chemical data is like a time capsule that preserves information about the conditions that prevailed in another star system billions of years ago. The isotopic analysis of 3I divided by Atlas can reveal the abundance of heavy elements in its home system, which in turn provides clues about the history of star formation in that region of the galaxy. The physical structure of 3I divided by Atlas, inferred from its rotation patterns and cometary activity, also informs models of planetary accretion. If the object formed as part of a protoplanetary disk similar to the one that gave rise to our solar system, but under different environmental conditions, the differences in its internal structure can reveal how variables like stellar metallicity or the intensity of the stellar wind affect the processes of planetary formation. This knowledge has implications that extend far beyond solar system astronomy. Improved models of planetary formation inform our understanding of the prevalence of habitable planetary systems throughout the galaxy. If 3I divided by Atlas is representative of objects formed in low metallicity star systems, for example, this could influence our estimates of where life is most likely to form in the cosmos. The observation campaign for 3I divided by Atlas has driven the development of astronomical techniques that will benefit the entire discipline for decades to come. The need to detect and characterize a faint, fast-moving object has required innovations in image processing, spectroscopic analysis, and observational coordination. The image stacking techniques developed to track the movement of 3I Atlas against the stellar background have improved our ability to study faint asteroids and trans-Neptunian objects in our own solar system. The automatic detection algorithms refined during the search for fragments and satellites of 3I divided by Atlas are finding applications in the search for potentially hazardous near-Earth objects. The coordinated observation protocols developed to maximize the scientific coverage of 3I divided by Atlas have set precedents for future observation campaigns of transient astronomical events. The speed with which follow-up observations were organized after the initial discovery of 3I divided by Atlas has demonstrated the effectiveness of modern astronomical communication networks and has informed plans for responding to future discoveries of interstellar objects. The spectroscopic techniques refined to analyze the anomalous chemical composition of 3I divided by Atlas are improving our ability to characterize exoplanets through the analysis of their atmospheres. The methods developed to separate faint spectral lines from background noise have direct applications in the study of distant worlds around other stars. One of the most important consequences of the legacy of 3I divided by Atlas is how it has informed plans for the upcoming Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope. This revolutionary instrument, which will begin full operations in the coming years, is designed to map the entire night sky every few nights, creating a time-lapse movie of the changing universe. The lessons learned from 3I divided by Atlas have directly influenced the automatic detection algorithms that the Vera C. Rubin Observatory will use to identify interstellar objects. The movement patterns, spectral characteristics, and prioritization criteria developed during the study of 3I divided by Atlas are being incorporated into the software that will analyze the petabytes of data the observatory will generate each year. The Vera C. Rubin Observatory could detect interstellar objects at an unprecedented rate, possibly identifying several each year. However, this abundance of discoveries will create new challenges. How to prioritize which objects deserve intensive follow-up with larger telescopes, how to coordinate global observations of multiple simultaneous targets, and how to process and analyze massive volumes of observational data. The experience with 3I divided by Atlas has shown that even with state-of-the-art technology, the time to characterize an interstellar object completely is limited. This has led to the development of automated observation protocols that can begin initial characterization of new discoveries immediately, without waiting for human intervention. These autonomous systems could be crucial for maximizing the scientific return during the era of the Vera C. Rubin Observatory. Although 3I divided by Atlas shows no signs of past or present life, its study has refined our understanding of how life could spread between star systems. The presence of complex organic molecules in interstellar comets suggests that the basic building blocks of life could be regularly transported across galactic space. The data from 3I divided by Atlas are informing models of panspermia, the hypothesis that life could spread from one planetary system to another through interstellar objects. While 3I divided by Atlas itself does not carry detectable living organisms, its intact survival during millions or billions of years of interstellar travel demonstrates that similar objects could, in principle, preserve biological material over cosmological periods. The techniques developed to analyze the chemical composition of 3I divided by Atlas are also improving our ability to search for biosignatures in future interstellar objects. Refined spectroscopic methods could detect complex organic compounds that might indicate biological processes, although distinguishing between abiotic organic chemistry and possible biosignatures remains a considerable technical challenge. The experience with 3I divided by Atlas has shown that even objects that show no obvious signs of biological activity can provide valuable information about the prevalence and distribution of organic compounds in the galaxy. This knowledge is fundamental to understanding the chemical context in which life emerges and evolves. One of the most important legacies of 3I divided by Atlas will be the permanent archive of observational data that will survive long beyond individual human lifetimes. This data, stored in multiple institutions around the world, will continue to be analyzed by future generations of scientists with techniques that have not yet been invented. The archives include not only the direct observations of the comet, but also the complete contextual data, atmospheric conditions during each observation, instrumental calibrations, the analysis codes used, and the complete documentation of all techniques employed. This completeness ensures that future researchers can reanalyze the data with improved methods or answer questions that we haven't even thought to ask yet. The images of 3I divided by Atlas will join the iconographic archive of astronomy, along with the first Hubble telescope images, the historic Apollo photographs, and the high-resolution images of planets taken by spacecraft. These images will serve not only as scientific records, but as visual testaments to the moment when humanity had its first prolonged encounter with a visitor from the stars. The spectral data from 3I divided by Atlas will become reference standards for for the analysis of future interstellar objects. The unique emission and absorption lines detected in this comet will provide templates for identifying similar chemical compositions in future objects, speeding up their characterization and analysis. The impact of 3I divided by Atlas extends far beyond the professional scientific community. The media coverage of the comet has introduced concepts of interstellar astronomy to millions of people who may have never considered the possibility that objects from other star systems regularly visit our own. The educational programs developed around 3I divided by Atlas are teaching students of all ages about fundamental concepts of astronomy, orbital physics, and spectroscopic analysis. The students learning about 3I divided by Atlas today could be the scientists who analyze the next interstellar object, or even those who design space missions to intercept future visitors. The temporary nature of the opportunity to observe 3I, Atlas has created a shared sense of urgency that has united communities of amateur astronomers around the world. Social media has been filled with images of the comet taken by dedicated observers, creating a distributed visual record of its passage through our solar system. Planetariums and science centers have developed special programs about 3I divided by Atlas that will continue to educate the public about interstellar objects long after the comet itself has disappeared. These presentations help contextualize our place in the galaxy and the dynamic nature of interstellar space. The experience of observing 3I divided by Atlas has provided a unique perspective on the scale and nature of the universe we inhabit. This object has traveled distances that defy human comprehension, has existed for periods of time that vastly exceed the history of our species, and has witnessed cosmic events that occurred before the Earth was habitable. Yet, paradoxically, our ability to detect, study, and understand 3I divided by Atlas also demonstrates the remarkable progress of human science and technology. In less than a century, we have gone from not knowing that other planetary systems existed to being able to analyze the chemical composition of objects that formed around other stars. This duality between our cosmic insignificance and our growing scientific power defines much of the modern human experience with the cosmos. We are simultaneously tiny on the scale of the universe and unique in our ability to comprehend that scale. 3I divided by Atlas has served as a tangible reminder of both realities. The finite nature of our opportunity to study 3I divided by Atlas also reflects the finite nature of many opportunities in human life and the history of our species. Just as this comet will not return in our lifetimes, many of the opportunities we have to learn, explore, and discover are unrepeatable and must be seized while they are available. As 3I divided by Atlas fades into the depths of interstellar space, carrying with it the secrets we could not decipher, it also leaves us with tools, knowledge, and perspectives that will shape how we approach future cosmic visitors. Its legacy is not only what we learned from it, but how its presence changed our understanding of what is possible and how we must prepare for the cosmic wonders yet to come. The children learning about 3I divided by Atlas in their science classes today could be the scientists who analyze the next interstellar visitors. The graduate students writing their theses on data from 3I divided by Atlas could develop the technologies that will eventually allow us to send probes to intercept interstellar objects during their journeys between the stars. The pioneering techniques developed to study 3I Atlas will evolve into even more sophisticated methods for characterizing the cosmic visitors of the future. The observation protocols established during its tracking campaign will become standard procedures that will be activated automatically with each new interstellar discovery. And perhaps most importantly, the experience of witnessing firsthand an object from another star system has permanently expanded our perspective on our place in the galaxy. We have seen with our own eyes that the space between the stars is not empty but filled with ancient travelers that connect all planetary systems in an invisible network of material exchange. When future generations look back at this period of human history, they will remember these years as the time when our species had its first conscious encounters with visitors from the stars. 3I divided by Atlas, along with Oumuamua, and 2I divided by Borisov will be remembered as the precursors that heralded a new era of interstellar astronomy, an age when objects from other worlds ceased to be theoretical speculation and became targets of detailed scientific study. The legacy of 3I Atlas will endure in the data libraries that will continue to be analyzed for decades, in the observational techniques that will improve future discoveries, in the inspired students who will choose scientific careers, and in the permanent expansion of the human perspective on our place in a universe full of wonders that we are just beginning to discover. And so, as the last ground-based telescope loses the faint signal of 3I divided by Atlas, amid the glow of dawn, we don't say goodbye, but until we meet again, knowing that although this particular visitor will never return, it has taught us how to recognize and welcome those that will follow. In the depths of space, other travelers slowly approach our solar system bearing secrets from distant worlds and ancient times, and when they arrive, we will be ready, equipped with the knowledge and tools that TESS and Atlas helped us develop, prepared for the next chapter in the continuously expanding story of humanity and the cosmos.